5.6 discrete dynamical systems. You'll notice I'm using a little bit of different technology here. I think I found a way that I can write on my iPad instead of having the camera shooting at the whiteboards. It's a little bit more work for me, but this section needed it because we need to show some pictures that I couldn't possibly put on the camera any other way. So what I want to do is, in 5.6, we're going to start by just having a little bit of a discussion on how we might think about a dynamical system, and that's a system where things are in flux and things are changing. And then over time, what are the long-term trends in that change? We kind of saw a little bit of a glimpse of this when we studied the Markov chains. And we kind of saw how, there's a little bit of flux from what happens today, and then after the same process happens over and over and over again, we see kind of long-term trends rising. So the question is, how can we make sense of those long-term trends in the terms of in terms of linear algebra? So what we're going to do is we're going to do this first half here on the computer, and then I have two application problems, and we're going to talk a little bit about the application problem, so a place where you might actually use some of this type of thinking. Okay, so to begin though, what we really think about is we think about some system here, and when we analyze our matrix, so we have some matrix A, and when we analyze our matrix, we're going to think of our matrix in terms of the eigenvalues of the matrix, and then their associated eigenvectors that go with them. So we'll have two eigenvalues and two eigenvectors, and the eigenvectors for this time are always going to be the exact same. I'm going to always have an eigenvector pointing in this direction, which is the eigenvector 1, 1, and then I'll have an eigenvector pointing in this direction, which is the eigenvector negative 1, 2. And so these are just going to be our two eigenvectors throughout the whole problem. And the real thing that we're interested in is in asking ourselves a question that looks like this. What if you just started at some point here, and we just took some value x, and this would be like an x bar, and then what if we just over and over again just took a and applied it to x? What would happen? What would happen is you would get some different value on your graph, maybe something like this, a x bar. So you would get a second value in your graph. Well, what would happen if we applied it again? We did a to that answer. So that would be a of x. Or if you like, we could think of this as a squared of x. And so a squared of x would show up somewhere else on our graph. And then we'll just keep doing this over and over and over again. And we'll have a n of x. And we'll just ask, what if we repeated this same process, did the same process time after time after time? What's the trend? And what you would see is you would see some trend of points, following in some way. And you could follow your values of a, and they would have some pattern to them. So what I want to do is I want to kind of go through and look at different patterns, and it turns out that the patterns all depend upon these choices. So they depend upon what are the eigenvalues and then what are the eigenvectors. And again, for us, we're always going to have the same two eigenvectors. One eigenvector is this eigenvector 1, 1, and the other eigenvector is this eigenvector negative 1, 2. Okay, so the first example is this, and as you can see, I plotted these on my computer, and so I just made it produce many different terms. And so here I've had 1, 2, 3, 4. I have 6 different starting points, and I asked what happens in the long term. Well, our first example, we have both lambda 1 and lambda 2 both being positive eigenvalues. And then we have lambda 1 equal to lambda 1 being a little bit bigger than lambda 2. And so the question is, what happens long term? Well, what you'll see is we have one of our eigenvalues is that vector right here. One of our eigenvectors is that one. And the other one of our eigenvectors was that one right there. And we can kind of start to see a little bit of a pattern brewing as we look closely. And I'll put one more shot where I'm going to turn these into lines, and you'll see these lines. And so here's the line of that if I were to take that vector and magnify it, and here's the line if I take that vector and magnify it. And what you'll notice is you notice that every point seems to be trending towards that lambda 1 eigenvector. So as I look here, you'll see that each point here tends to be trending towards that lambda 1 eigenvector, and they're all kind of towards be bending that way. Why is that? Well, that's because lambda 1 is bigger than lambda 2. And then here, they also tend to be kind of trending in a general pattern towards that eigenvector. And if you were to stretch these out long enough, they would eventually have patterns that kind of look parallel to that line. They're kind of heading in that direction. Let's think about why that would be the case. Well, what if I had picked, say, a point on the eigenvector? What would happen? Well, since it's an eigenvector, it would stay pointed in the same direction, and so you would end up getting just a straight line. And so those points would be in a straight line, and lambda would tell us how much bigger those points are. So it would just be getting bigger and bigger according to whatever lambda is doing. And so if you think about some other points, some points near that line, then what they're going to do is they're going to trend kind of towards that line and kind of even out and try to follow it nearby that line. Now what you'll notice this other eigenvalue is doing is it kind of forms some sort of separation point where things on this side of that eigenvalue are going to be negative in respect to that second eigenvalue, and so they're going to trend towards the negative direction of this lambda 1, and versus things on the positive side of that eigenvalue will kind of trend towards. So you see how our eigenvalues have kind of separated out the plane, and then each point kind of trends in the general directions of those points. Okay, so now what we'll do is we'll make one of the eigenvalues negative and see what happens. Now what you'll notice, if I made lambda 2 negative, things that start out close to lambda 2 end up kind of hugging close, kind of end up going down in a negative fashion. Why is that? That's because the lambda 2 values are getting smaller every time, so they're kind of moving down my axis. Whereas the lambda 1, the ones following that first eigenvector are going up the axis, so they're kind of going that way, versus these values that are kind of going that way. So what you'll notice is that if you start here, you come down and then you kind of approach that one and you go out. Versus if you were to start on this side, you would come down and then you would approach and then you would kind of move out. So you kind of have this sort of pattern, and so you can kind of see the pattern for each one of these points where they're starting, and they're each one are kind of approaching the positive eigenvalue and going away from the negative eigenvalues. And the negative eigenvalue is bringing them down towards the origin, and then the positive eigenvalue kind of pushes them out from the origin in the direction of that eigenvector. Okay, now finally, what happens if they're both negative? Well, if they're both negative, what happened there? Okay, let me work. Okay. There we go. Let's come back. That one died. Why did that one die? Okay, let's come figure it out. Let's just start the presentation. Okay, here we go. Sorry about that. I'm still figuring out the technology. As I told you at the very beginning, these aren't all professional. Okay, so what happens if they're both negative? Well, if they're both negative, then every eigenvalues on the red line are all approaching the origin, and values on the blue line are all approaching the origin. So it doesn't matter which one you point, it approaches the origin. However, it continues to kind of approach according to these eigenvectors. So in this case, it kind of approaches, and then it kind of ends up taking that eigenvector approach as we get close to the origin. But you can see when the eigenvalues are negative, everything, no matter what it is, kind of collapses in towards the origin. All right, now what happens if we have complex eigenvalues? Well, we saw in the last section that we could think of complex eigenvalues as introducing a rotation. This notation here means the magnitude of lambda, so this is magnitude. So if the magnitude is equal to 1, then that means the size of the eigenvalue isn't changing the size of our points. So you notice that no matter where you start, that you end up following in some sort of circular fashion, so you end up being rotating. Now what you'll notice, however, is that our eigenvectors are giving us some sort of picture of the rotation. And if you remember, this eigenvector was an eigenvector of size 1, so it was that eigenvector right here, or 1, 1, so it had a magnitude of square root of 2, and this one was 1, negative 1, 2, so it was that sort of eigenvector right here. And so you can see that this eigenvector was a little bit longer than that eigenvector. And that gives you a little bit of an idea of why the rotation would be elliptic, and to be elliptic with these eigenvectors going on them. If you see this gray, if you see kind of this gray path here, you'll notice that it hits kind of both this eigenvector, and it kind of hits really close to the negative version of that eigenvector. And then it hits close to this eigenvector and then close to the negative version of that eigenvector. So you notice that the eigenvectors are kind of pointing out the shape of the ellipse, and they kind of go in the direction and around these two eigenvector coordinates. So the complex eigenvector, so a complex eigenvalue makes things have rotations involved, and the magnitude and the eigenvectors kind of give you some picture of the plane or the orbit by which they take. Now, what if these have a magnitude that's not equal to 1? So first, if it's a positive magnitude, what you'll see is they still have that same orbiting picture. So you'll notice that it has kind of that same rotation, but what's the difference? The difference is the magnitude gets a little bit bigger every time, and it spreads out. And so it kind of spins out bigger and bigger. So it's a spiral, but it's an outward spiral. What if it's less than 1? Well, if it's less than 1, then we have the same type of thing, except now it spirals in that same kind of elliptical orbit, but this time it spirals inward. And so we see that these two eigenvectors are giving us the shape. The two eigenvectors are giving us the shape of the spiral, but the fact that the complex eigenvalues are less than 1 means it spirals inward on itself. Okay, so the last thing I want you to do is come back and look at the next video. And so in the next video, we're going to tackle two problems. We're going to tackle these last two problems, exercise 5.33 and then exercise 5.34. And these two problems are both what you might call predator-prey problems. Actually, I don't think the second one has a predator, but it kind of still fits the same type, predator-prey, or you might say a population model. And so the idea here is that we have some sort of populations, and those populations are changing and have some sort of behavior over time. So once we see the behavior of those populations over time, can we tell something about the long term? Can we predict something long term about those populations? How big will they be? Will they grow? Will they shrink? And things like that. And what you can see from this exercise is that the relationship of the populations will depend upon these eigenvectors or eigenvalues. If they're less than 0, that means our populations are going to shrink. And if they're greater than 0, that means our populations are going to grow. And so that kind of gives us some picture of what we can expect to see. All right. Thank you very much. And I will see you on the next page when we go back to our whiteboards for the very last video we're going to make covering material this semester.